everybody on the panel so far, except for, I've forgotten your name, Steve from 23andMe is a speaker here today. I saw Steve from 23andMe. For those who don't know, who are not from our part of the world, 23andMe, well, you can explain what it is, Steve, very quickly, what 23andMe is. Oh, you're mic'd up. Yeah, we should. Yes.
Okay. Yeah, so 23andMe is a direct-to-consumer genetic testing company. You go online, you buy a kit, you spit into a tube, and in a few weeks you get results. We give both like ancestry information, so who you're related to, what your ethnic background is, and also health information, risks of certain conditions, traits, things like that.
So it's a commercial, if you like, it's a commercial application of a science project, which was really the sequencing of the human genome, and this is sort of a commercial thing. So the panel consists of, I've got two practitioners, Steve and Ben, both in the science phase. I've got two technologists, Brian and Alkis, who actually build stuff that they care about. And Sujit is here because we have to have an academic to lend the panel sufficient gravitas. So what I'm going to be doing is I've got a series of questions I've thought through, but this is meant to be interactive. So if you hear something that you disagree with strongly or you agree with strongly, hold your hand up, I'll bring you the mic and we can clarify. So look, the first thing I wanted to talk about is that, and this has been true, each of the practitioners that's been up talking about their particular piece of the puzzle, the elephant, the sort of the Hindi myth of the many wise men sort of trying to figure out the elephant has come back. Everybody appears to have a different kind of abstraction. Jupyter Notebooks has a Python abstraction, Panda data frames, and so forth. The SQL abstraction, the world I'm from, has tables, set theories, set relations. There's a machine learning, which talks about linear algebra. That's come up multiple times. And I wonder what the panel's reaction is that what I'm hearing is I'm hearing that we haven't got the abstraction right for machine learning. We don't have an abstraction to reason about data, to present data to machine learning algorithms in a way that's intuitive for it to work, for them to work with. And we appear to have a, if you remember the 1990s, there was this idea of an impedance mismatch between client tools, object languages, and databases. We appear to have an impedance mismatch between the way we do data organization and the way we do machine learning algorithms. And I wonder if the panel wouldn't mind each of you, starting with Ben on the left and going through to the right, commenting about the question, do we have the right abstractions in the software layer? Do we have the right tools for interacting at various layers of the stack?
Yeah, definitely. I think that's an excellent. Is this on?
I hope so.
Is this okay? Yeah, good. So I think that's an excellent question, and particularly in my field, this is a big challenge because one of the biggest stumbling blocks between using modern machine learning techniques and state-of-the-art is just the format of the data and how it's encoded. So we have in HyNRGFigs our favorite data format. And it's not.
I'm sorry, you said that a bit quickly. Which was the favorite data format?
Oh, it's a really obscure data format called root. You've probably never heard of it.
No, I haven't.
And we've written our own C++ libraries for doing everything. And it's really a shame because there's all sorts of open source tools that are used. I mean, they're open source within our community, but you would never pick up a HyNRGPhysics tool and use it for anything. So I think it's moving towards making things more compatible with standard data formats, HDF5, NumPy arrays, these kind of things. But we're, so far, it's kind of like moving very slowly in that direction. And I think this is something that we have to learn how to use better in order to gain from the community and also provide back to the community as well.
So the idea being that in specialized areas of science where what you want to have is a specialized format, indeed for specialized algorithms, there's an argument for making that. And the problem, or the observation, is that this precludes the use of a lot of other tools. HDF5 is one, NetCDF fits formats and things like that as another. Interesting. Sujit, what's the academic take on this?
Yeah, so I'll provide a little broader and high-level response. So one of the things that we see is that machine learning and deep learning, I'm just learning techniques, are becoming very, very pervasive in everything that we touch. It reminds me when I have a computer science background, and so programming was a privy of computer scientists. This was a long time back. And then over the last 2 decades, a mechanical engineer or an artist, everyone was supposed to be working with computers and being able to do some coding. This is where I think I'm seeing machine learning going in every different areas that we are touching, from networking to wireless communications to medical science research, to anything that we are seeing in the campus. People are using machine learning. So if it is to be so pervasive, the question is that how can anyone who doesn't really have the expertise of machine learning use machine learning? And so I think that there are two missing pieces today. Well, in academic research, we are using a lot of open source tools, right? Open source software and so on. One of the things our students and our researchers do a lot is try out various standard machine learning models and also deep learning models. They are more and more available. So the models are available. So from an abstraction point of view, what I think is missing for for quick research is the interfaces with cloud and database. Because most of the data that we gather, store are in the clouds, various forms of cloud, and so how can we make the use of these models very, very easy for all our students and researchers and our faculty, by having easy accessibility or integration with cloud and databases is one thing that I'm seeing missing. The other thing that I'm seeing missing is that in various different areas, for instance, we have started working on smart transportation projects, autonomous vehicles. So we have these simulators, and combining the simulators with these machine learning models or access to data is sometimes becomes very, very difficult, almost a nightmare. So those interfaces and those abstractions are also missing, and I'm hoping that as the use of machine learning becomes pervasive, that people will be working on figuring out how machine learning interfaces with simulators. There are various kinds of simulators that we need to interface with.
So just to put a pin in it, one vote for the democratization of machine learning. You're seeing that much more broadly spread, and an inhibition or a factor that's constraining that is exactly this lack of abstraction, this difficulty for the communication collaboration. Alkis, you're hip deep in this, so what's your take on the abstraction problem within Google, for example?
So I don't want to make any predictions on the right abstraction. My hypothesis is that we're likely to find a good abstraction if we look at the way that the end users are dealing with the data and the problem. But it is also important to find the abstraction at the points where different layers communicate with each other, right? So if we insist on using, a relational database system can be very powerful in churning through lots of data, but we cannot insist on using SQL or SQL abstractions to do that. I think Sujit basically echoed some of that in his presentation. At the same time, if we figure out a way to take what the user is doing on a notebook and translate it to something that a relational system understands and can do efficiently, I think that's sort of the best of both worlds.
When you say relational systems, so relational systems, SQL systems are famously built around an algebra, a set theoretic algebra. Now, I guess just to sort of to poke that gently a little bit, the abstractions that a Jupyter Notebook would support, the abstractions that are supported by some of the work we saw earlier on large-scale linear algebra and matrix algebras are a different abstraction. So is the key thing, just to sort of ask a clarifying question, it may not be SQL it may be SQL as a kind of a, how to say this, there may be a select from there somewhere, but what's in the from clause, the table functions, the algebraic building blocks that exist in that declarative framework may not look much like what SQL 92 looked like circa 1995. Is that roughly where you're thinking, or is something
absolutely.
else?
So I guess I'm thinking of the relational system as an execution engine, right? At the end of the day, you can give it a declarative specification of the computation, and might not be pure SQL or SQL 92 as you mentioned it, right? But I think the important part is that you need the declarative specification so that the system can understand how to optimize it, right? And maybe the interface doesn't end up being SQL 92, maybe it's something more extended, but it's still beneficial to go down the route of declarative specifications. And Since you mentioned impedance mismatch, I think that for me, one excellent example of how we were able to sort of work around that impedance mismatch was Link, the work that came out of Microsoft, where you had a SQL-like interface embedded in the programming language. And this worked very well in many respects.
Very good. So there's a vote for an abstract algebra of some kind, which we can optimize, which we can provision, which we can work with, but not necessarily the same sorts of algebras that we're working with today. It may not be either an array algebra nor a set theoretic algebra, but some weird melange of the two would be the reasonable characterization?
Yes, and I think that it's important to maybe not expose that algebra to the end user.
Yeah,
because
agreed.
a data scientist or somebody who's trying to solve something with machine learning doesn't necessarily want to understand a new algebra, right? They already have an environment in which they feel familiar and productive. And the challenge is, can you take their intent as specified in that environment and translate to that algebra so that the computation can happen efficiently?
Very good. Steve, abstractions within genomics.
Right. So first I'll echo what Ben said about the file formats. Bioinformatics has its own set of custom formats for various purposes. But what's on my mind more recently? So we are a company that has both a research portion of what we do and a web application, consumer facing. The impedance mismatch for me is that there is between those two environments. The researchers develop the models using their set of tools and on their own data sets, so data sets that have been anonymized, for example, to take results from their analysis and put that into a production setting is difficult. It takes you can do some things with technologies like Docker to make sure the computing environments are roughly similar, but then there's issues with the data stores where the production data store might be a completely different system than the one that is serving the scientists. Maybe they have a copy of the data on their local machine. So for me, like figuring out how to take results from this sort of research exploratory analysis and plug it into a production system is a difficult problem, and that's for me where the impedance mismatch is.
Very good. So that would suggest that perhaps the abstractions that are being used on the desktop are insufficiently abstract and that they can't then be generalized to production environments.
Yeah, like the details of data stores and data processing, cleaning, all of those are they're not, right now they're not sufficiently abstracted that you can just take something from one environment and plug it into another.
Very good. Brian, the obvious abstraction is Jupyter Notebooks and Python. Would you disagree with that?
Actually, a lot of my thinking on this comes from my background as a physicist. So I've spent most of my academic career teaching physics and recently teaching data science and machine learning. And so my thinking about abstractions, even in the Jupyter context, comes from physics. And there's a huge contrast between the level of abstraction in physics. And I think it's important to realize that the sophistication and the maturity of the abstractions in physics have emerged over multiple centuries. And from that perspective, we're still at the very infant level of abstraction in machine learning and data science. And the thing that stands out to me as sort of abstractions develop is that in the history of physics, you can see how physicists often were asking the wrong set of questions, or were asking a set of questions that were not ultimately the right ones. A great example is during the development of Newtonian mechanics, physicists and others were asking, how might we predict the motion of the planets? And there's an implicit assumption there that the observable of interest is the position in velocities, right? Turns out in quantum mechanics, that's really not the right question to be asking. What you want to ask instead is, what is the state of the system? How does it evolve? What are the observables? And I think we're still at the age right now in data science and machine learning where we're trying to figure out what the right questions to even ask are. And judging from the sort of history of physics, we're just barely at the beginning.
Very good. So a computer scientist asks a question about abstraction, expecting an answer in the language of APIs, and Brian picks it up and punts it to the moon and says, no, you've got to think about the sort of meta questions that scientists have to ask and answer. So that's a very good response. All right, I'm going to now lean in a little bit on a slightly provocative question. This is one that when my friends, I work for Teradata, I'm here to help you, but when my friends in the commercial space sort of talk to our clients and customers, and when we read our blog sites and when we sort of look at the world, this is sort of a provocative observation, but I was pleased to hear Steve sort of backed it up a little bit. What we're seeing among our customers is a tremendous kind of fecund growth of people who are doing data science. So people are being hired as data scientists, they're being given access to distributed file systems, to Jupyter notebooks, and so on and so forth. When we talk to the sort of C-level executives, there's, and if you sort of pardon the expression, there's butkus in production, that people are able to find insights in private data sets. But as Steve says, when you try to take a model that's generated by a financial customer of ours to do default prediction in a portfolio of mortgages, when you try to take that and then apply it in the field, there seems to be a big gap there. So I'm wondering, in the view of the panel, and we'll start with you, Brian, and then move back to the right, what is the inhibition here? Why aren't we seeing more applications of machine learning and deep learning AI techniques going from the laptop and sort of into more frontline productions? Modular, by the way, there are cases, the Netflix example, where there's clearly a business there that's built around a very vertical specific, where the research question kind of is the production question. But in a lot of cases, we're seeing situations where the research question is interesting and answered, but then it's difficult to turn that into sort of, get any return on that investment from a purely commercial point of view. So Brian, left to right, if we could just respond to that, hopefully not too provocative thought.
Yeah, I mean, the big thing that stands out to me is yes, data scientists are expensive relatively to hire, but compared to the realities of deploying models in production, hiring data scientists is probably relatively cheap and easy. And I think the production side of it gets to be very difficult. I see that even at like universities that have a lot of data that could be used in a variety of ways. And it's conceivable they might be able to hire data scientists, but building a full-blown productionized system for training models and actually getting stuff done regularly with those models is likely really expensive.
And if you could wave a wand and do two things to change that, what just and it doesn't, what would that be? What would the changes be that you'd make?
Yeah, so I'll respond with a provocative answer. Very good. That is, as has always been the answer, anytime there's a major revolution in the tech world, it will be built on open source tools and technologies. And so whenever we get to the point where we feel like, yes, productionizing machine learning is something that we have solved and we all can do, we will look back and say, there was something like Docker, something like Linux that came along, something like Kubernetes that came along and enabled everyone to do that at a scale not possible previously.
So that the answer is going to be that, or not the answer, but our response is that this is going to require a community kind of contribution, some sort of open source project or framework that is going to sort of help sort of fill these gaps.
I'm not referring necessarily to the mode of, to being community, more that the technology is developed by a set of stakeholders who are not primarily concerned about capture. And that's
good answer.
At least not at the beginning.
Very good, very good. Steve. And again, I'll just preempt, I'll wave the wand and change two things. What would they be? At the end of your answer, I'm sorry.
Sure. So when I think about machine learning as a field, it requires a diverse set of skills. There's linear algebra and math and statistics on one end, and at the same time there's There's software engineering, architecture, where you have to build these large distributed systems to store the data, make it accessible. Finding someone that can span that entire range of skills is very hard. You're looking for unicorns. And so I think one of the difficulties is finding those people, but that's probably not going to change. To get the expertise in all of those, you're spending a lot of time in school and things like that. So I think as much as like these different domains, can make their parts easier for non-experts to use. I think that could be something that makes it easier to productionize these things. If I could wave my wand and change two things, I guess one of them would be for scientists who want to go into machine learning and data science, crossing over and getting some software engineering skills, even things like version control systems and writing good code. That's not part of most curriculums. I know like when I was in grad school, we never talked about code quality at all. That is a big obstacle to getting production systems, is having this version control, collaborating with people in a distributed repo or something like that. The other thing I would change, if I could wave my wand, let's see. I don't know if I can think of anything off the top of my head.
You don't need to give two. Curious, we've had one vote for improved sysops, one vote for improved DevOps, just as a thought. Alkis, what would you change apart from the capitalization of Google?
So I think that, or at least I've seen two, let's say, obstacles to taking a model that is built as an experiment and bring it in production. I think one has to do with what Steve mentioned about experiment management, or the impedance mismatch, I think you named it, where the environment in which you build the model is very different than the environment in which you do the production. I think there we need better tools for experiment management, so that we understand what changed when we went from experiment to production, and we can go back and iterate on it and see if we can fix the model. But in other cases, I think the problem starts much earlier, in the sense that a model necessarily deals with a very specific objective and question, and maybe that is the wrong question to ask to begin with, right? So you might be optimizing for a very specific loss metric over a very specific aspect of the data, and it turns out that when you go to production to solve a much bigger problem using machine learning, this is the wrong piece of the data, and this is the wrong loss function and the wrong objective overall. So I think I would like to take a cue from databases and see if we can come up with more declarative approaches to machine learning, where we can start by asking, what is the end goal if we were to put this in production, and then work backwards and see how would this translate now to more concrete machine learning abstractions that we can throw machine learning at, right? And if we have that link from the end goal to the lower level machine learning abstractions, then we can go back and see where we can fix things that are broken.
One vote for sysops, DevOps, experimental ops. Sujit.
So you meant it to be a provocative question, so I'll try to be a little provocative.
Yes.
But I'll not answer initially as an academic, I'll answer as a user. I'm not saying this because we have someone from Netflix, but I think that Netflix, when they used machine learning to create the recommendation system, they did it right. It's divided up into genres and so on. But I recently subscribed to a music service. I'm not going to name which one. And I just wish they had not implemented a recommendation system, because any item I touch, they are thinking that it's something that I'm liking, and they're just going completely haywire with their recommendations. It doesn't matter whether I like the song, don't like the song. They just are coming up with hundreds and thousands of recommendations. That's not the way to do recommendation, right? So I think that we are not ready. And in that case, I'm pretty much waiting for my next cycle, and I'm going to desubscribe and try out some other service where it's going to be simpler, better, more effective, more personalized recommendation. So now going to the other hat, We work with a lot of industry partners. We are using machine learning to develop various different applications in AR, VR, in connected health. I presented some of the things yesterday in smart transportation, autonomous vehicles. I think that in either of them, as much as I love our work and our colleagues' work, we would not recommend that they be commercially deployed yet. And the main fundamental reason is this. Well, there are two reasons. One is that I don't think we have to do much when in transfer learning and online learning. The data that we are collecting, great data, but when we try to commercialize it, the data that we will get to see, for instance, in connected health, the kind of patients and so on, might be very different. And we are very good in machine learning, and I think very, very sort of at a very initial stages in transfer learning and online learning. We need to become much better, to safely and securely deploy these things commercially. The other thing is that, so I attend various different kinds of data science platforms, events, and we don't talk much about what are the consequences of failures, what are the consequences of errors. And so we need to do much better in terms of, in some areas, in images and videos, it is well known that classification techniques using machine learning, deep learning are still not at the 80%, 90% accuracy level. In some areas, deploying might not have as much consequences, bad consequences, right? But imagine deploying something which has a 90% accuracy in health sciences or in autonomous driving, right? What are the consequences of false positive and false negative? So we need to be much better at what we are doing. We need to understand that what are the plan Bs. So if predictions are wrong, sometimes it adds, let's say in AR, VR latency, which is fine. It's jitter, it's a little inconvenient experience, that's fine. But sometimes it's about security, privacy, safety, and so all those aspects we need to bring in. And I don't know how long it will take, but we need to have honest discussions about, and it's a very good question that you asked. It's a very relevant question, not provocative question.
Very good. So I'll just, I have the opposite story, which is that about 2 years ago, I went online to look for mattresses, and I bought a mattress within a week because it was obvious. The Google recommendation engine continues to insist to give me ads about mattresses. I bought a mattress. I'm not going to buy another mattress for the rest of my life probably, but you insist on showing me ads for mattresses. So it's the opposite case. I am the classic false negative. Anyway.
Right. But it's essentially you are corroborating what I'm saying, and that is it has perfected one aspect, but it hasn't perfected the human aspects, right? Yeah. That you don't need it anymore.
It doesn't matter that I'm being constantly told to buy this mattress, but being told to take this particular diabetic drug over and over and over again could have dire consequences. Ben, again, why aren't we seeing a CERN? Why aren't we seeing a hadron collider in every home? And what would you, if you had a magic wand, what would you wave and change?
You could have one for the small price of $10 billion.
Yeah, the check is in the mail.
Great. No, I think, so we do have some machine learning algorithms in our production systems for identifying, for online processing as well as offline production. We definitely don't have a challenge engaging the community. Like there was a Kaggle challenge just released today for high energy physics to do charge particle reconstruction. But I think the key challenge that we have is that in order to make that Kaggle challenge, we had to abstract the problem enough that it was basically remove all the physics from the problem,
right,
and make it simple enough that it could be solved, in a standalone way. And then suppose someone, I hope that someone has a really brilliant idea to solve that problem. But then backporting that into a production system that we can use, I think will be a really big challenge. And I think part of the challenge is that a lot of that backporting is not interesting. We're adding back in complications, trying to get it work in the technical frameworks that we have set up. And we have a problem also with code sharing. We have, I have 3,000 collaborators on the same experiment as me. It's an aging code base, and these are the usual kind of problems. But getting some of these state-of-the-art techniques to work in practice is really not glorious, very important, and very technical. And it requires knowing not just the machine learning, at least what the machine learning is supposed to do, but what the physics is and how the structure is around that aspect of the code that's being changed.
So another vote for DevOps and also a vote for domain expert ops. We need to sort of make those work better.
Yes.
All right, well, one last question because we're butting up against lunch, and we'll keep this one very, very quick. If you, each of you on the panel, if you had to identify one technology, one piece of software, one piece of hardware innovation that you were not involved in that you think deserves more kind of publicity, very quickly, what would that be, and where would folk go to find out more? We'll go right to left this time. So Ben, starting with you.
Hardware, software, what was the question?
Whatever. If there's name a piece of technology, a piece of something that you are aware of but not working on that's professionally relevant, that you think should be given a bit more airtime, a bit more sort of play.
Oh, that's a really difficult question.
You can pass, or we can come back to you if you prefer
I'll
to
pass.
think about that. You pass.
Yeah, I'll think. Yeah.
Something from, because I think I mentioned this question to you. So
Yeah. So I cannot say that we are not absolutely involved, but this is our aspirational goal. We think that it's very, very important. So in the modern age, where is the data being collected? It's at the sensors. It's with the mobile devices, right? So the collectors of data are becoming more and more these IoT devices, these mobile devices, and so on, right? Of course, their numbers will be in the, I don't know, I don't want to take a guess, but somewhere in the trillions and so on. So when we think of machine learning, when we think of AI, when we think of databases, when we think of computing, we need to move down to, to these edges. And we need to start thinking that, how do we, so computing is definitely moving towards the edge. We call it edge computing, we call it fog computing. Computing has to merge with AI techniques, and like computing is now becoming very, very pervasive in our networks. If you think of 5G networks, it's going to be inbuilt computing everywhere. And so we need to think of how AI and databases are built into the network. We don't want to go all the way to the cloud and access and come back. It's just going to be too much data transfer. So how can we totally rethink and redesign our machine learning techniques, our databases, and everything down to the edges, and whatever the edge means. Edge can mean various different things.
So this is Mike Franklin at Berkeley and AmpLab had a project that was the Edge database project a few years ago. So things of that nature, being able to, it's not a distributed computing or distributed database framework, but rather it's almost like an operating system environment that allows us to sort of push code and data around in ways that make sense. Very, very provocative idea. Alkis.
So that's a difficult question. I think I'll answer a different question. Anyways, I think I'm super excited about the applications of machine learning in healthcare. And I know this is not the question you asked, but I guess at the end of the day, we all have, as the prototypical application of machine learning, recommender systems, and there are the song recommendations or the mattress recommendations that don't go away. But if we can actually improve something so fundamental about human existence as healthcare, I think that's fantastic. So I think I would like to see more and more of our efforts and resources being poured into this kind of applications.
That's an application with teeth in it, as my joke this morning was. Steve.
Yeah, so I haven't heard a lot about this. I'm sure people know about it, but I guess like technology, I think, is not getting enough credit is containerization. So if you've heard of Docker, that's the most prominent one. That really allows customizing the environment that you're doing data analysis, data exploration, model training, model evaluation in. Historically, I remember SSHing into scientific computing clusters. You had to live with whatever version of Python was installed on the system. If there wasn't a library installed, you had to, file a ticket to get it installed. Containers let you install whatever libraries you want, and you can even then pack that image up and send it to someone else, and they can recreate the analysis just by running this container. So similar to like how Jupyter is sort of, it packages the notebook together. The container packages the entire environment, And, and then in combination with each other, you see this very commonly now that they're used together to give some of these reproducible analyses, cross different, organizational and environmental boundaries to allow machine learning to go on.
A vote for Kubernetes. Brian.
Yeah.
So in the Jupyter world, people want to look at data. And so I'll give an answer along those lines. So Jeff Hare's group created D3 with actually here at Stanford with Mike Bostock. And they've gone on to create 2 other projects, Vega and Vega Lite, which are declarative grammars for visualization. In particular, Vega Lite, which targets sort of ggplot style statistical visualization. There's a new version out of the Vega Lite specification that includes really rich interactivity, zooming, panning, cross-filtering type of interactions. And we're seeing a lot of take-up and excitement around Vega Lite in the sort of Jupyter ecosystem.
That was Vega, V-E-G-A, as in the star?
V-E-G-A-L-I-T-E.
Very good, this, as in the star, which is also one of my favorite stars. Back to Ben, for the closing comment and a piece of technology that you think deserves more time in the sun.
So yeah, I give a second vote to containers. And as a related concept is something we take advantage of is like opportunistic computing. So both on HPCs where we use the HPC version of Docker Shifter and other, like for instance, we have like a program where we can use, people can sign up to on your computer when you're not using your computer to run LHC analyses. I think these kind of things, like we're computing limited right now, and there are other fields I know that are computing limited. There's a lot of computers out there. So maybe these kind of tools can be used to help spread around the love and make the science more powerful in the end.
Very good. A vote for the group in Berkeley who were doing the search for extraterrestrial intelligence,
yes.
the SETI framework.
The SETI group, yes.
Peer-to-peer, they used to call that peer-to-peer computing or peer-out computing. Thank you very much. We're up against, did anybody have any questions for the panel quickly? Otherwise, we are between you and lunch. One to pass on.
Hi. With machine learning, the question that I have is sort of about antagonistic feedback from the real world. Like physics probably doesn't change because you started using machine learning, but people watching Netflix or healthcare would actually change their behavior when the machine learning models change. So do you have any comments on how to handle the influence of the world back into machine learning when you apply a model?
Iterative machine learning that learns.
Yeah, that's a very good question. And so, for instance, a couple of things, right? One is that's why we are emphasizing more on discovering online learning techniques, because as you recommend, and in various different areas, eventually it's actionable machine learning, right? So the actionable intelligence leads to some kind of recommendation. We can call it recommendation, we can call it various things, and recommendation leads to a human reaction. And you rightfully pointed out that changes the behavior of how we do things, how we get data, how we buy things, and so on. So it's a constant learning process, and I think that as we do better and better in this continuous learning, but also learning from peers, then it becomes more effective. I'm not sure whether I completely answered your question or not.
So this is questions about the observer effect. We observe some we observe some particular facet of human behavior, but as a consequence of the acknowledgement of that observation, the behavior itself changes, and that means we've got to the wonderful chaos of our existence. Come on, somebody else has to have a stab at this. You've stumped the panel. You get to take home the mini-moke. All right, we're all low on blood sugar. I'd like you all please to thank the panelists again. That was I learned a lot anyway.